Okay, hello everyone. My name is John Osborne. I'm an assistant professor here at UAB, and I teach the natural language processing course in the computer science department and the biomedical applications of natural language processing course. Today, I'm going to talk about reinforcement learning with human feedback. That's going to be the main focus of my talk. It's sort of the secret sauce in ChatGPT. And for people looking for CatGPT, I know they proliferate, you're going to be disappointed. There's no cat memes here. Just focus on ChatGPT. So what I'm hoping to teach here today are for people who don't have a lot of experience in NLP to learn what a language model actually is and give folks sort of a high level view of transformers, which underlie all the modern language models. And the main focus, though, will be reinforcement learning with human feedback. I have put together a tutorial, which is in GitLab. Hopefully people have access to. Some links will pop up during the talk if you don't have access to that. So you can go through that tutorial and actually do some reinforcement learning with human feedback yourself. And then at the very end of the talk, I'm going to give an overview of sort of where I think this is going in terms of these large language models and ChatGPT. Okay, so we'll do the sort of fundamentals portion of the tutorial first, just giving some definitions for language models and terms like gradient and embeddings that'll be thrown around a little bit. We will talk about GPT-2 and GPT-3. They're both very similar, really just a size difference, and ChatGPT is based on those. And then the sort of new content for people who haven't taken my course will be the RLHF stuff. There's the link there on GitHub. If you don't have that already, it should be available to you. You can actually go ahead and start the tutorial if you are already, an NLP expert and you don't need to hear about the fundamentals. You haven't forgotten anything about GPT. You can start it right now if you want to, and do it during this talk. And at the very end, I'll talk about the future of where I think these language models are going, the importance of data, model size. There's a mini demo that I really like for people who are interested in doing that. It requires less technical skills than running the tutorial in Google Colab. There's a link for that here as well. And then I'll talk about GPT-4, which is already out there, and we've already seen a little bit of that already today, and possible healthcare applications. And then there should be some time for questions and discussion at the very end. I've never given a 90-minute talk before, so I'm expecting to have a little bit of time at the end, but we'll see. Okay, first, all the hype. So it's hard to kind of get away from it right now. There is so many possible applications for ChatGPT. How many people have heard of ChatGPT? How many people have actually used ChatGPT? Got the description? So it looks like about half the people, if not more, have actually used ChatGPT. So you've heard of some of this stuff, I'm sure. It's got a big impact on education, how we're going to, grade essays and that kind of thing. It's passing medical exams. It's affecting not just, sort of science stuff, like with, abstracts that are being created and entire papers that it can generate. Science fiction as well. One of the magazines actually cut off acceptance of new science fiction articles because it was getting so much spam that it couldn't tell very easily if it was real or not. And the AI song came out recently, not really ChatGPT, but the technology is similar. So it's definitely been in the news. So I'm going to start with the most fundamental thing here, which all these models are, which is a language model. So what actually is a language model? Because it gets thrown out a lot. And this is the definition from Wikipedia, which is accurate. It's a probability distribution over a sequence of words. Has input a sequence of words, and if you can output a probability, you have a language model. And when I first heard this a long time ago, I thought, man, that's really dumb and totally useless. But actually, it's incredibly difficult challenge. To actually figure out what's going to come next in a sentence, as I'm talking here myself, you have to know about the syntax of the language. What are the semantics? What's the context of the language? There's a lot of things that if you want to learn a language model, you have to pick up about the world and about language. So it's actually an incredible task. And the beauty of it, of course, is that we have a lot of data for it. Anytime someone writes a book, records a conversation, anything computer can process, it's massive amounts of unsupervised data. Okay, so this is my mini little diagram on language model taxonomy. So there's a distinction made sort of between statistical models and neural models. In some ways, it's a little bit fake because there's lots of stats involved in neural models, and we'll talk about some of that today. We talk about KL divergence. You're calculating means on layers and neural networks. But the statistical model is sort of the old style model, would be like a bigram model. And the neural models can kind of go into two classes. On kind of the bottom left here is sort of non-generative models. So this is like BERT. People may have heard of BERT, came out in 2018, broke a lot of different benchmarks. But the focus today, we're going to talk about these generative models right here, like the GPT style models that actually generate text and are sort of in that way real language models rather than mass language models. Not that these don't have a role here, and they're actually better than generative models in some cases with equivalent size. So like I said, we have these statistical models. They've been around for a while. They're n-gram based, and that n-gram means like it could be a bigram, two words together, trigram, and you can compute statistics on those. One thing they'll always do is they'll have this sort of Markov property, sort of like, how far back you're going to look. There's sort of K right here. So if you had a bigram model, you're only looking back, 1 right here. If you have a trigram, you're kind of looking back 2. And the reason is that you don't have that much statistics on 4 grams or 5 grams. They occur very uniquely. They're not that informative. So you typically have a bigram or trigram model. And the thing about these language models is they never really played a central role in NLP. Yes, they were useful for some tasks, but you could do a whole bunch of things and never, involve a language model at all. The neural models aren't that way. And they kind of came out of the deep learning revolution in the 2010s. Initially, they are these RNNs, which are recursive neural networks. I'll talk about that briefly. Like LSTMs and GRUs, but now it's all transformers. And so they may or may not, provide that probability distribution, but they can certainly predict one, and you can, basically replace any language model with them. So the other word you may hear is foundational model. So that's like GPT-3, GPT-4. These are these big pre-trained models that people are talking about. Okay, so we're just going to kind of set the stage for ChatGPT here. Talk a little bit about neural networks, word vectors, transformers, the attention mechanism really, and the sort of GP2, GP3 architecture. So this is like 4 lectures in my course. So I'm going to go through this thing, in like 15 minutes or 20 minutes or so. So apologies for that. It should give you those sort of a high level view. People hear me? Okay. All right. So battery died. It's okay. We can continue. So it's going to be, unfair to people that don't have a lot of experience with this, but it's probably the best we can do in the time that we have. Okay. So neural networks have actually been around, at least conceptually, for a long time, all the way back to 1943. They're not really relevant anymore, but sort of the core features are still there. Neurons are still going to have, these weights right here, and they're still going to take some input. There's going to be a bias to that. And even the sigmoid function up here, if you're doing some kind of binary classification, that's still used. So that hasn't really changed so much. We do now have, though, other functions like or activation functions like the ReLU function, very simple function, max of 0 or x, but it's cheap to compute. And there are a lot of other ones as well. I'll talk about the softmax function, which is sort of used like the sigmoid in multi-classification. There's GELU functions, for example, a little more sophisticated, versions of ReLU. So these have been around for a while. And oops, okay, I can't really. Just checking if I can look at my notes over there. That's fine. can skip over that. Well, let me go back to here. So we have these, neurons and these sort of mini neural networks here with just one layer, but they weren't very good for a bunch of different reasons. One of the reasons was they couldn't compute arbitrary functions, like XOR, for example. They need a linear separable function. This was solved, by having, multiple layers. And so that's why when people talk about deep learning, they need these multiple layers so you can compute arbitrary functions. And the other thing, they didn't really know how to train them efficiently. So this was eventually solved with backpropagation, which again would be many slides in my lecture. And the idea basically is that instead of having, your X1, X2, you have sort of an XY input coming into your little neuron right here. And you're going to compute your activation and be able to make your inference. And then you're going to have some result that may be, predicted value. It's going to be right. It's going to be wrong. Let's suppose it's wrong. You want to be able to compute basically the gradient, which is sort of the loss with respect to whatever the input was. And that's going to flow all the way from, the top of your neural network all the way back down. And you're going to kind of apportion blame basically. So here, you can calculate the loss with respect to X, this input, loss with respect to this. So if you're severely wrong, you want to know how to update the weights. You want to maybe update it more, and you want to know which particular neuron was responsible. So this is not a bad link. This explains backpropagation, like 5 levels of difficulty. But when you think of, gradient, just think really it's just for people that are calculus, it's a vector of partial derivatives. And because we're going to have a large number of neurons, it's going to be basically a huge matrix of all these partial derivatives. So this is sort of the intuition of it. So you have, your input right here into 2 layers here in our neural network. Make a forward pass, do our inference, predict some output, and we'll have our actual answer. And then we're going to do backpropagation using the loss function, probably cost entropy loss, and do a backward pass and update the weights of all this for training. So that's how we're going to train neural nets. The same, whether you're doing ChatGPT or BERT or whatever other neural network. There are some other newer methods than backpropagation, but backpropagation is still sort of standard method of doing that. Okay, so we solved the problem about how to train these things, but it really didn't take off until a little bit later. And but why we use them basically is one is the representation. These huge neural networks can really represent complex linguistic phenomenon. And that means instead of having a bunch of hand engineered features that you create, you'll actually learn them from the data. And the other thing that of course made them popular is they got great results. First in vision, they started winning contests. And then NLP, once it had transformers, it kind of started its own golden age. So the things that made it possible are the cheap GPUs, the word vectors and the representation of words, which I'll talk a little bit about, transformers, then BERT winning a bunch of things in NLP, and now ChatGPT. So focus on a few of these. First, word vectors. I'll use the word embedding sometimes. So embedding is really just itself a word vector, so a dense word vector. Previously, for words, people had used sort of one-hot encodings. So you think of a vector with 100 elements maybe, but there's only one element in there that is actually highlighted, on a different dimension. So you can have your apples and oranges, maybe the first element is 1 for apple and everything else is 0. And for orange, the first element is 0, but the second element is 1. So not a really great representation for words. So people learn these sort of classic word embeddings. These are things like glove or word to vec. They're nice and they have some interesting properties, which I'll show on the next page. Though people now will use, a little bit more advanced embeddings where it's not just co-occurrence statistics, like, word to vec, but the actual position matters. And no word embeddings are the same. A lot of complexity is hidden behind that. When you load up your model, for example, in the tutorial, for people that are doing the tutorial, you're bringing in a bunch of word embeddings. It's not apparent. And all those word embeddings are the result of training on a particular corpus. So if you are doing something with social media versus something in clinical text versus biomedical abstracts, you need to really have the right set of word embeddings. Even things like tokenization scheme will adjust those. So if I say embeddings, I'm talking about dense vectors, basically. And this is one of the many sort of figures that I've just thrown on here is that's showing about word embeddings. There's a lot out there, but this is showing the basic sort of compositionality property of word embeddings. And you can see here, sort of a man and woman, and you can see the same sort of relationship between king and queen, same vector, sort of a gender, male, female bias, verb tense, you can have country and capital. So you actually have very sophisticated word representations. So sometimes you'll read like popular articles saying, well, these models don't really understand anything, just a bunch of statistics. But if you think about it, if you look at the word surgery, these kind of word models could tell you about, the use of, the gender and how gender relates to surgery over a time period, probably better than a surgeon could even, because it's read, all these different books. So this gives you a numerical answer. So they're actually quite sophisticated. Okay, this is one of those auto-selected from PowerPoint Designer. I think they always pick this one for transformers. So I'm going to talk about transformers, but I'm going to talk about it in sort of the GPT-2, GPT-3 context, so I can set you up for ChatGPT. So this is going to give you sort of the origin story of transformers, which will help you understand them. So they're really a replacement for these RNNs. This is recursive neural networks. So they were called recursive. So this is an RNN right here and here and here. They're recursive because they're taking in their own input. So this particular figure grabbed from this paper was doing translation. So you wanted to have, encode basically, say, a French sentence right here. So it would encode however many words there are until it got to this sort of, end of sentence token right here. And then it would output, an embedding, basically representing what, this sentence was in French. And then it would go ahead and the decoder would output, what the translation is going to be in English, going along until finally it decides the next most probable thing to output is an end of sentence, and it ends the translation. So that's a decoder and encoder. Yeah, that's about, let's say about that. Okay, this is another famous picture from the Transformer paper. Again, I'm going to go over it relatively quickly. So because we have transformers, we don't have this sort of RNN anymore. One of the things we're going to do is we're going to take our inputs. These are going to be our word embeddings that we're talking about, input embeddings. We're going to do this kind of positional encoding. So what that really is you have your word embedding, but you're going to actually basically give it to a bunch of sign functions that basically multiplying by where that word occurs in your input phrase. So, you multiply it, by, if the very beginning would be 0, the very end for GPT-3, I think it's a 2K embedding, it would, 247, times whatever, all these different sign functions you're pushing it through. So you have basically a positional representation combined with the sort of input word embedding to give you your representation for your encoding. There's also going to be multiple layers here, and the layers, now we're not going to actually use encoders for GPT, but they're here in the paper, so I'm just going to talk about them a bit. It's the same on the decoder side. You can have any number of these layers, and the more layers you have, the more sophisticated your representation is going to be. And I'll talk about that in the next couple slides. The feed-forward neural network is just like that perceptron I showed earlier. It's a fully connected network. So that means that every neuron in layer 2 is fully connected to everything in layer 3. And that's to learn sort of this representation right here. And then we're going to do, we have these residual connections too. These are kind of jumping ahead, where you basically add in the input that was put in here to the very end as well. So you kind of keep some additional information that you may have lost when you went through that attention head. And then also the normalization here, you're doing a layer normalization. So instead of averaging all your values for the batch, you average across the layer, and to learn a little bit better. And output dimension size for this model is 512. Again, it's like 2K for like GPT-3. And then the decoder has this little extra sublayer that's gone. So if I was going to draw the GPT or 2 or GPT-3, I'd kind of get rid of this extra bit right here. But you do have this mask multi-head attention that you don't have in the encoder. I'll talk about that masking a little bit later. Anyway, it was efficient to train. So that's the sort of basic transformer. The attention mechanism, we have kind of an intuition in English what attention actually is. Really here is just this mathematical operation here. This Q is sort of one word in your sequence, and it's being compared to everything else in the context size that you're looking at to figure out that's the actual attention right there. And then it's scaled down here by the size of the model, so you don't get too big or too small for these weights. And then you multiply again. Actually do a soft max on here first. So if you have a particular word, it could point to which other words in the sentence, for example, it thinks are most relevant to it. So that's sort of the attention mechanism, English language description of it. And then you multiply by the V here. So once you have the attention over all the words to get your output. That's a compatibility function. Scaling feature. And these are all just the input coming in. So all taking the same input, K, Q, K, and V are all input from your sentence. Those are embeddings. And then it also has this sort of multi-head attention feature. So you could learn, one matrix, but instead they learn, multiple, depending on how many heads it has. This is another important parameter when setting things up. So you can actually focus on different things in a sentence. And I'll show you that in the next slide. You can maybe focus on, dependency relations in one layer. Earlier on, you may be just focusing on the previous word. So you have multiple ways to show your different attention. And you learn this projection, during training. Nothing forces it to learn it, but it will learn it. It's just easier for it to train that way. So this is GPT-2. I'm just showing you two different layers here. There's layer 4. You can see that it's kind of attending to the previous word, and then layer 1 looks like it's kind of faded out a bit, but it's looking at everything else that kind of precedes it. So you learn different aspects, and you can have many layers. It doesn't be 4, it could be 12, it could be 64 or thousands of layers. Okay, so that's the basic transformer. So how does GPT use that? So like I said before, GPT is just stacking the decoder portion. And again, without that second layer. This is from Jay Alamar's blog, which is a really nice one for looking at GPT-2. And they really just differ by the size. And so if you had GPT-3 here, it would be even larger. So here, I know it's like 48 for GPT-3. I think it's like 96 or something like that. So just basically larger size. And the self-attention mechanism, just a little example of that. So when BERT, this encoder model looks around, it looks around everywhere at itself, everything in the context. It's going to mask like 15% of these things out. So we'll have to guess and predict those things. But with the mass self-attention, it has this sort of left to right nature. So it can only look at the preceding tokens. That's what makes it great for generation, though, and it has to learn what this token is going to be. And it's auto-regressive. So once it predicts this token and then it knows about it, then it can go ahead and predict this token using this token's information. That's why it's a generative model. It's this mass self-attention component here. And so this just gives an idea of, the sort of development of the sort of, pre-ChatGPT models here. You can see the, obvious trend, going from 117 million parameters in GPT-1, about 10 times that in GPT-2, then increasing again by the same factor here. Same thing with heads, and this context size as well. This is basically the span of the attention window. So, if you want to be able to reason over larger documents, you really want to have this context size as long as possible. So GPT-3 is better at that. And then again, the hidden layer size, and batch size are all just getting larger and larger here. This is a huge number by comparison. And the more training data as well. So from 5 gigs to 40 to 45 terabytes. Okay, so how am I for time here on ChatGPT? Okay, so now ChatGPT. So before I talk about ChatGPT, I'm going to mention InstructGPT, which came out the same year. So this is the paper that really has the RLHF details. They used a lot of annotators to generate data. It's fairly substantial. ChatGPT itself, we really don't know that much about it. People, have used it. I use it myself, but there's no paper really that describes it with the model. You can't really download it and use it. You don't really know what data it was trained on. We know it's a really big, expensive data set, and we know that it's similar to InstructGPT, but we don't really know too much about it. So I'm mostly in this talk, when I talk about RLHF, and I'm going to talk about InstructGPT, which is also by OpenAI. It's really, maybe this is the best picture I saw that kind of describes the difference here. So I talked about GPT-3. So InstructGPT has this sort of RLHF built on top of it, focusing on being able to be helpful and give instructions. And then ChatGPT has this sort of like safety RLHF, we think, training on top of all that. So that's kind of the difference here between these three models. So the RL stands for reinforcement learning. So this is a review for people who don't know that. I have done until I did this talk, I had done basically no reinforcement learning. So the idea with this is that you have an agent, got a little beaver here, that does some action, and that action, changes the state of the environment, and he gets some kind of reward or not based on whatever his action was. So the policy here, which we'll talk about, is basically a function that maps, a particular state to an action, and it can be basically anything. Okay, so where does this RLHF fit into sort of the things people may know about already? So this is sort of the sort of standard way to do things. For a while, people have these pre-trained language models, could be BERT, could be GPT-3, whatever, GPT-2. And you have this sort of supervised set of training data, you fine tune it, and then you have some great prediction on some particular task. That's kind of the standard way of using these language models. With the larger language models, with GPT-3 is really what got the ball rolling on that, is you would actually just take this pre-trained large language model and ask it to do something for you, like without any special training. So there's no prompt tuning, no extra data. It's like a zero-shot prediction task, and hopefully it does well. It'll do worse than fine tuning on basically anything, but you don't actually have to do this. So that's why it's considered to be great. And then you have the sort of, the few shot where you maybe have a little bit of minimal data that you can provide for your examples. And you can do few shot prediction, and it does a better performance than zero shot. So RLHF is actually much more complicated. And that's why I got all these arrows kind of floating around here. There's gonna be multiple models that you're gonna have. You're gonna have some pre-trained language model that you're going to use. You're also going to, and you could actually use a fine-tuned model to start with as well. There's going to be two of them. One you're going to, use as your baseline, like either this one or this one. And then you're also going to have, a reward model as well. And then you're going to train basically this new RLHF model. So you're going to have 3 different models. And the idea here is that you could do prediction on a wide range of tasks with this, not just, like one task really well, or kind of, no specialization at all, but like sort of a wide range of tasks. Okay, so for people who are doing the tutorial that actually want to today go ahead and run their own RLHF stuff, you can go ahead and load up the tutorial. Basically, my tutorial is I took the, so TRL is a library that Hugging Face put out. They have some example code there. It's a Python file. And I basically kind of tweaked it to make it work in Google Colab. So you could, in the space of, this talk, actually run it yourself. There's no Chiha. I like research computing a lot, but I think it'd be potentially overwhelmed. So you can run this in Google Colab. So this is just really maybe a different description of what I've already been saying. So you have this sort of initial language model right here, which is sort of like your baseline model that you can you'll start with that can generate responses. You have an evaluation model framework. This is your reward model, completely separate language model that spits out these little scalar values telling you how well or you're doing. So basically a reward. And then we have this really complicated optimization process. We're going to use the same baseline model here in conjunction with the model you're actually going to train. And you're going to teach this model to respond to human feedback. You're going to get log probabilities for these sentences and compute KL divergence, which I'll talk about later. And all that's going to go into reward, and you're going to update your policy, which is really just fine tuning. And until you keep taking your active model and it gets better and better, and it becomes a ChatGPT or an InstructGPT. So for the tutorial, make sure you actually are using your notebook settings, are set to using a GPU, and load in your required libraries. Just if people often forget to actually load that in. If you don't know where it is, just go to Edit and Google Colab, and you can adjust your notebook settings and just pick GPU. The models that I put in there are small enough you can run it during this. Should not be a problem. The other thing you should do if you don't have one already is get a Hugging Face account. So you'll need that because you're going to want to have this user access token for yourself, so you can copy it in, so you can actually access these models. It's probably a good idea to get a Hugging Face account anyway if you're doing any of these kind of modeling stuff. So get one of those, because the way I set it up is it'll prompt you actually for the access token, and then you can give it to it before the optimization step, essentially. Okay. So what's the motivation for all this reinforcement learning with human feedback? So there's a technical motivation. So when you train a language model, you're training with next token prediction loss as measured by cross entropy loss. So it's not a great metric because you can have all sorts of issues with that. So if you had like some example corpus and it said, P53 guards the genome, to give a sort of biomedical example, and the language model 1 said, pizza guards the genome, and language model 2 said TP53 guards the genome, you're actually not getting, TP53 is much closer. It's the gene instead of the protein, should get, higher points, but the way the metrics work, it's not going to get it. It's going to get the same, or it's going to get worse, depending on how it tokenizes that TP53. So you really want sort of a more human metric. And we have some metrics like Blue and Rouge, but they're really not that great. Actual humans are much better at saying whether the language is appropriate or not. So that's kind of the motivation here. And also there's this, what they call the language model alignment problem. The idea that, predicting the next token on the web page is just different from what users actually want, which is you want to, helpfully and safely follow the instructions of the user. So RLHF is an attempt to kind of align these two different things together. There's also obviously commercial motivations for doing this. With ChatGPT, the goal really was to have something that's less toxic. And we know, and there's actually this famous paper that came out, and I think Timit Gerbu here, she was actually fired from Google, but just kind of, it's actually a very reasonable paper if you read it, but just pointing out that if you have, this huge data sets, it can't help but encode all the biases that we have in our society. So you kind of want to remove that. So you have a more friendly language model, one where ChatGPT won't necessarily insult you, for example. And for InstructGPT, the focus was on being helpful and honest. Again, things that you want a language model to have. But again, if you're training on data from the internet, I know folks are shocked, but not all the information on the internet is true. So you kind of want to have a truthful, helpful model. And so RLHF can help with that as well. Okay. So how does it actually solve this problem? Well, for fun, I decided to ask ChatGPT for me to see if it would solve the problem for it. And I did the classic one where I asked it to explain like I'm 5 years old. And it's actually a really impressive explanation. You know, it talks about, you know, a robot friend learning to play a game where you get, you know, treats or rewards when you say the right thing. So it's actually, for people who haven't seen ChatGPT before, this is the kind of stuff that it can pull off pretty well. So I'm not sure I could have written such a great explanation for a 5-year-old as ChatGPT did. Yeah, so that's sort of like, for any 5-year-olds or less in here, here's your ChatGPT explanation of how this stuff actually works. Okay, so let's dive into sort of this 3-step process of how RLHF works. And every now and then I'm going to reference some of the code that I put on GitHub as to how to actually do this. So you can check that out as well. So the first thing is actually, you know, collect demonstration data and train a supervised policy. So they have a prompt data set, you know, at OpenAI. We don't really know what that prompt data set is because they haven't released it. So for fun, I'm showing you another prompt data set on the right-hand side here. This is from MedAlpaca. There's a whole thing going on with, you know, animals from the camelid family, but I'll show you the picture of that next. But this is just some prompt data from a bunch of different sources that MedAlpaca has used, which I'll show on the next page. And once you have these prompts, you can actually, you know, train a nice supervised policy. So here, what they had is they actually had the humans go ahead, they look at the prompts, and then they actually demonstrated the desired output behavior by having that human write, you know, what the actual, what they would call response or continuation actually is. And they did this SFT. This is just normalized. This is just the normal sort of fine tuning that you do for any language model. Doesn't really involve any, you know, special, you know, reinforcement learning, anything like that. This step is actually optional. So here's the link to the MedAlpaca here. So if you want some prompts for medicine, people may be interested in this, you can actually grab all this stuff. They list all the different data sources they have here. A lot of things related to medicine, but also questions from, you know, Stack Exchange, Chat Doctor, all those types of stuff. There's like a big JSON file in there called like medicalmeadow.json or something like that. And you can look at that. And if you want prompts, if you want to try this yourself for some task here at UAB, I recommend that. Again, like I said, this whole process is actually optional, but I think that the idea is to get sort of a better starting point for your language model. So it's already good at, you know, giving appropriate responses out. So if you have that, that'd be great. For our tutorial, they didn't, and I didn't actually, you know, have this, you know, kind of training data. So we're just going to use basically a GPT model right here called GPT Neo 1.3 billion parameter model. So you can use any sort of initial language model you want that you're going to end up doing RLHF on. Okay, so we're skipping this basically in the tutorial, the short answer. Okay, the reward model thing. Okay. So we want to collect data for basically the reward model. So this time, remember before we had that prompt data set. So here they're actually generating the prompts from their, they're giving you the prompts from the prompt data set, but they're outputting all this, instead of humans outputting what the correct response is, you have a bunch of different models outputting them. GPT-3 basically in the case here for InstructGPT. So you have a whole series of different, you know, explanations of, you know, what the moon landing is like for a 6-year-old. And then the label, instead of having to write out that explanation about people going on the moon or whatever, they simply just rank all of the different explanations from the different models right here. So the ranking thing is nice because it allows for comparison. And by showing that, and they showed them all to the annotators at the same time. So you can imagine if you were given some kind of annotation task and said, hey, rate this between 1 and 5 or 1 and 10. It's really hard to do and be consistent about that. But if you see the rank, it's actually much easier to use. So if you do any of this, I think this is probably the smarter way to go. They're very intentional at how they did their annotation here. So there's definitely some tips to be picked up from that. And so then, it's blocking me off here. Yeah, so then we have all this data now. And again, we just train a reward model. And again, nothing special about this is normal sort of language model fine tuning that's going on here. So those are the two sort of the more straightforward steps for RLHF. Okay. And they did ranking here, but it actually doesn't have to be ranking. You could do anything else. You could do ELO. It doesn't have to be. It could be binary even. That's what we're going to do. Anything that kind of outputs a scalar should be good enough. And the size of the reward model itself, it can be large, can be very large, can be smaller. There are 6 billion parameter model actually work better than the 175 billion parameter model. So the size of this reward model isn't clear how large or small it has to be. I think that's still to be discovered. For our tutorial here, I've just copied some code over here. We're going to use this this one from Facebook, I guess Meta now, the Roberta hate speech Dynabench R4 target. That's going to be our reward model. We're going to load that in. So over here. Here it's going to call the generate function. For those of you not familiar, the generate function is the sort of Hugging Face standard for their language models. You call generate, and it outputs some text. And you can play with these parameters a little bit. These are the ones that were assigned on the sort of the original Python script, but you could tweak this around a little bit. Here, just picking, it's basically how you're going to search for the response. You can pick, the top K parameters. If you want, how that was 5, you could pick the top 5 responses to look at. Top P's were sort of a summation of probability. You could adjust those as needed. So the training data for this sort of Facebook model that we're using for a reward model is shown here. They had like multiple rounds of training, so 4 rounds, and they initially just did like, is it hate or not hate, and then later on they actually broke it down to different categories, so what kind of hate it was. But for the actual model here, it's just binary 0 or 1 for training this model. Okay. The really tricky step for this is the optimization step. So it's definitely the most difficult to understand. So probably spend the most time on this one. So step 3, and again, these figures are all from the InstructGPT paper over here on the left-hand side. Again, you're going to take that prompt from the prompt data set. They had their own different data set from people submitting things and whatnot. We're going to use a different data set called real toxicity prompts, which I'll show on the next slide. And the way it works is the state basically is sort of the input prompt that you're starting with, and then you're going to give it to the language model that you're training here. And that policy is basically going to output an action, and that action is just a continuation. It's just some additional text that's created after the prompt, hopefully something that is desirable for the humans. And then you're going to have your reward model separately calculate a reward for that, some output value. They're going to use that reward basically. It's got some other stuff in there too, but this reward to go ahead and use that to train and fine tune our policy, which is just our language model here. So that is the step. And I think I have another example of that here too, showing that. But first, the real toxicity prompts. So if you look at this, these are the prompts, and they don't actually have anything necessarily bad in themselves, but they're kind of setting you up so that it's likely that it's going to start generating sort of some toxic content. So you want to sample this data and see if your language model will take the bait and start writing some toxic content out there. And so they have these prompts, and they use this Perspective AI, I think it's commercial software, and basically gives like a toxicity score to all these prompts here. So you know how good or how likely are to induce toxic responses from language models. Okay. So in our tutorial here, we're going to load in these toxicity prompts from LNAI is where it's coming from. And then we're going to go ahead and sample these prompts. I guess the motivation for this, I'm not sure where the 30 to 40 came from. I guess maybe that was empirically derived. They figured out that, these are a better size for prompts. But you want to have a variety of different prompts going in there from the data set. So you're not, if there's any ordering to the data set, you want to get rid of that. I presume you have a sort of more random uniform sample for training. Okay. And then the other thing here, you're actually going to filter this through to make sure, you exceeded your toxicity threshold, this 0.3 right here. Because there's no point in feeding a bunch of prompts into your data set. They don't generate any toxic stuff. You really want to have that. So you're just tokenizing this and then pulling out all the other samples through here. Okay, so this is, I'm crossing out some of the stuff, but I'll go back to the stuff that I blacked out for a bit here. So PPO is proximal policy optimization. It's actually originally based on summarization. The version they use is just maybe a little different in InstructGPT, which I'll talk about a bit, but they use gradients basically from the original language model. And so it's nice because you can run in parallel, so it's easy to parallelize if you have multiple GPUs, and it's on policy, meaning that you only update the parameters with sort of the current batch. You don't keep any kind of buffer or list of things. So you just keep updating with whatever the current input is. So it's like an online training algorithm. You could deploy this in an online fashion to keep updating your model if you had, continuous input coming into it. Okay. So how does this work here? So if you look at this here, you're getting your you have all your different prompts here. And then when you're calling PPO trainer.generate, it's actually generating the responses. So this is like generating the actions for your agent in reinforcement learning. And if you looked earlier on, I think there's a configuration option where we showed that there's actually two models. So you're actually generating one for your initial sort of baseline model, and you're also generating text from the one you're actually training, your target model here too. So that's what's happening right there. And then once you have those responses generated from those prompts, maybe they're toxic, maybe they're not, you're going to, put that response into toxicity inputs. I think we're missing it here, but on the next slide, I think we have it where they'll actually feed into the reward model. You can generate up to max new tokens basically for your response. Okay. So the other thing that you're doing as well, remember we're generating there's two different models here, right? There's this initial language model, which is frozen. We're not changing this thing at all. And the target one here, we're actually training and it's learning the RLHF stuff. This is the one that's going to be fine-tuned all the time. So you have two models and they're going to output text. You can think of that as two different distributions of text that it's putting out there. So we're going to actually compute KL divergence. So just looking at, how different these two things are. And the motivation behind this is that you don't want to have the model just generate, junk or gibberish to kind of like, show that it's, generating non-toxic stuff, but it's just junk. You still want to generate reasonable looking, sentences. And so the KL divergence is basically saying, I want you to do better with the helpful, less toxic output, but I don't want you to change the model so much that you don't generate, reasonable sentences anymore. And in InstructGPT, they actually add in the gradient from the initial language model as well when they do this updating. It's not really PPO, it's PPO PTX or something with the gradient in there. And so, so the actual training process, you have the reward, you're getting the value about how toxic that is. You have the KL divergence, you're adding them together, and then you're going to basically, try to minimize the negative reward. So you're not changing the model too much, but you're pushing it to be, more helpful, less toxic, or whatever your human reinforcement is. Okay, and then we have to update the model. So here, I grabbed this from, I think this is the guy who maybe was involved in it, because there was a Medium page where he had written some things. So, what is the reward here? So, you could have used just the label neutral. By neutral, they mean like non-toxic, but that didn't work very well. So they actually used the logits. So for machine learning talk, that's sort of like the values that go into your softmax function, sort of near the end of the network before you compute your class probabilities. So those actually work better to use as a reward. So they use the logits here as the reward. And then you're going to do this step procedure right here. And that is actually where you're doing the whole fine tuning process and updating your target model. One other question is, how much data do you need to actually do this optimization? And the kind of answer is, how hard is your problem? It's definitely less than the huge amounts of data you use for pre-training a language model, but more than supervised training, maybe. So there's some examples here for some of these other models, how much they actually use, how many examples they actually used. The stuff I wrote in the tutorial for how long to train for, I didn't want to train for too long. So I kind of put some junk in here. You can adjust that yourself. I played around with, the size of the models and, batch size and whatever else to see how long things would take. It would take a while to go if you ran it all the ways, but I just broke off after a few epochs here. So the sort of smart way to do it is you could checkpoint your models and then see how well they do on a validation data set and then pick the best one. And that's what InstructGPT did when they were trying. I got muted somehow. Okay, thanks. So where is this all going? So things are happening very quickly, but I think there's some trends that are worth talking about. One is data has always been important, but there's actually more importance on the data now, perhaps than before, on training data, training it for longer, and training hopefully with data that can be shared. I'll talk about Llama and Alpaca. And then smaller, more efficient, but functional models. I'm going to talk about LoRa a little bit for that. And then the whole multimodality, we already saw some of that earlier today with Steve Jobs and Elon Musk having a conversation. That's going to be a big thing. I'll talk a little bit about healthcare applications for this as well. Okay, so the data. So this was an interesting, this came out, I think, at the end of last year. So they basically experimented training with more data rather than having a larger model. They did some other things as well, where they actually made the model smaller by changing how they stored the weights. Instead of like 16 floating point 16, I think they did like int 4 or something like that. So they could do, we have a smaller model, it's much better. I mean, you can do inference, it's much less costly. And what they showed here with this, if you look at some of the results, this is the, on this side here, this column is like the parameter size, how big the model is. So the Llama model, even with 33 billion parameters, is outperforming, these Palm models and these Chinchilla models, which are much larger, parameter sets. So I think that's encouraging because, as an academic in a, small lab, it's training this stuff is very expensive. So to see that, maybe just some more data, but not these huge requirements for memory. That's kind of good to know. So I think we'll see more of that. I think we already have this year. So one of the problems with this Llama stuff is, this is Meta. They didn't release their data, right? So that's a little bit frustrating. But folks from Stanford, they released a different version called Alpaca, kind of playing off Llama there. And this is basically InstructGPT right here, this text DaVinci 003 figure from their paper. They actually managed to generate a whole bunch of prompt data using something called self-instruct. So basically they manually did a bunch of seed tasks right here, 175 seed tasks, and basically just kind of snowballed it using the language model. I'm not going to talk about this too much, other than to say that they could do it for basically like $500 and something dollars. They managed to do this, generate all this huge prompt data set, which they made available. They did fine tune this, but I think there were some restrictions on, they're allowed to have it, I think, because they're Stanford or something, to make the Alpaca 7 billion model, which you can download from Hugging Face. Just pointing out the importance of having actually public data so you can actually replicate these models. This one is from yesterday. I just threw this in here. So this is another issue with data that's going to have to get sorted out. This was a fake interview. They had it with Michael Schumacher, who's been in a coma, I think, from a ski accident. They had this whole article, an interview basically posted on this German tabloid, and his family is now suing him, and really just mentioned at the very end of the article that it was AI generated. So it sounds like some kind of issue, but maybe not relevant for healthcare. It's actually really super relevant. So this is so topical. I got this in my inbox. I'm part of the AMIA, which is the American Medical Informatics Association. So I get all the group emails. So got this note saying, oh yeah, if you're using Mimic, you can't just throw it into a model like that. So how many people here are actually using the Mimic data set from PhysioNet besides myself? Anyone else? Nope, maybe just me. I know there's a couple of people on campus who are using it though. So you have to be really careful about this, following the data use agreements. So you can't just, throw in someone else's data when you have a DUA and put it into your language model. So it's the don't share, basically, prohibit sharing with third parties email I got. This went out to the whole group, not just me. So the other encouraging trend, I think, is the smaller and more efficient models. So one thing is LoRa. This came out, I think, October 2021. And it's basically a way to do training, but with a much less trainable parameters. So normally when you train, you're going to adjust like all the weights in your entire language model. And if the weights are large, really huge, that's like a lot of stuff to update. So what LoRa does instead is said, you don't have to actually, adjust all these weights. Let's learn this other, matrix here, BA instead. So this is actually, to get this, they do a singular value decomposition on this. And then they basically compute like a low rank approximation. And by low, it could be like as small as 2. You're thinking, oh, well, they lost so much information in that. But some of that information may have been noise anyway. And they say they get equivalent performance here just by training these two other matrices here. This is just initialization here, normal distribution and 0 for this one. So this is applying LoRa basically to the Roberta model, people may be familiar with. Roberta's got like 125 million parameters, not that big of a model these days. But this Roberta base LoRa, 0.8 million, tiny by comparison, but fantastic performance here that they're showing. So a lot of the new models will involve LoRa as well. Same kind of thing you're seeing with Roberta as well. So I think that's very encouraging. Another thing that's happening too, people are getting much smarter about how they actually train or do inference on these language models rather. So there's all these different tools out there. The one library I recommend is this PEF library from Hugging Face. You can do LoRa with it, can do other things as well. The tutorial here uses Accelerate as well. So you can do sort of a low cost inference. So push a lot more things through there. For people who are interested and didn't want to do the whole tutorial, but want to have like their own sort of ChatGPT on their desktop, this is a fun little thing right here. You can actually run this whole language model like ChatGPT, not quite ChatGPT, of course, but it's actually sort of a smaller version of that. It's basically Stanford's Alpaca instead, the one I was just talking about. And you can download it and run it. It's very easy. It fits on your your laptop. So if people are interested in doing that, they can. Just showing you that you can actually have a lot what the size improvements are like. Okay. The other thing that I'm super excited about, I was talking to Matt Might about this before the talk, is the context window. And just remind people again, this is sort of the length of text that your transformer is looking at. So, stuff started off with very small, like maybe 256, tokens that you're looking at. But it's really exploded. I mean, ChatGPT, which is sort of like the 3.5 one you see here, didn't have that many, but GPT-4 has a lot more. I think a big part of the improvement of GPT-4 is the fact that you have this much larger context size. There's an 8K model, there's a 32K model. So what that means in practice is like, people would have all these hacks basically to get around these small context windows. There's things like Longformer and Big Bird that would just look at partial attention over the sequence. But if you have the larger model, you can look at the entire sequence. So if you're, say, processing clinical text, for example, that means you can read the whole note in there, do inference over the whole note. If you're reading, papers on PubMed, they're just putting the abstract in there and looking at it, because that's all that'll fit in there. You can read the entire paper with your GPT-4 or whatever, and get reasonable results. So if you look at some of the ChatGPT stuff, if it's trying to look at a scientific paper, it's not going to get the citations right. That's just too far outside the context window. It'll make it up before hallucinate it before it actually gives you the correct answer. But if you can actually have these larger context lengths, there's a lot more reasoning that can happen. And I'll show that with some results we have here with GPT-4. Grab this from Forbes cover. It's kind of cool. So I'm mostly going to be showing results for GPT-4 because that's all I can show, sadly. So there's not like there's a paper for GPT-4, which I'm going to have some figures from that, but there's no details about the architecture, including the model size, hardware, training, compute, data set construction, training method, or anything like that. So this is kind of big black box, So, but the capabilities are, what it can do are of course available. And if you have a Chat or a GPT Plus subscription, then you can actually use it, and it's really quite impressive. So here is some of the results, and this on the left hand side here, these are kind of standard kind of NLP benchmarks that do different sort of NLP tasks. Multiple choice questions, and 57 subjects. HelloSwag is common sense reasoning, grade school stuff, coding tasks. And if you compare GPT 3.5, which is what ChatGPT is based on, there's just a massive improvement. And just like anecdotally, if you have used GPT-4, not everyone has. How many people have used GPT-4? It's significantly better than ChatGPT doing these kind of tasks. And this is a huge thing. I feel like it's another sort of burnt moment in NLP where all the work you've been doing for the last few years, someone just did better than you in like everything. And so you could probably just publish a paper right now if you wanted to. You could take whatever your task is, throw it into GPT-4 and show you just beat the state of the art on whatever data set you ran it on. So it's that much of an improvement. And so give some idea of how much better it is. This is the example I took from like the GPT-4 paper. So it's kind of hard to read this text here. But the guy over here is saying, our learner overgeneralizes. So, let's, minimize structural risk, rework our loss function, make the next kernel stable, unbiased, and use a soft margin, all this stuff. And then this guy's like, stack more layers, but unironically. That's kind of how it is right now. We're just dumbly stacking these layers, and all that kind of smart physics stuff is like that. So it's kind of funny. And what's amazing, the punchline is this is GPT-4 actually describing why this joke is funny. So, and it's actually a really good explanation of why the joke is actually funny. Most people wouldn't get it unless they know a little bit about statistics and a little bit about machine learning, but actually, outputs quite a reasonable response as to why the joke is actually funny. And the other point I want to make here too is, so this is a picture, right? So this is multimodal. So GPT-4 is doing all the multimodal stuff. So right now, with this paper, it was just images, but we know it can do video. We know all the other multimodal stuff is coming as well. So it won't just be restricted to, text. We're moving past that. I have this as well, which is sort of the scary version. I have time to play this or not? It's like 1 minute. I think I can fit it in here. So this is actually AutoGPT, which is based on GPT-4. So let's play this one.
Welcome to this brief demonstration of AutoGPT. Today, we'll be showcasing the AI's learning ability by asking it to research information about itself. Let's begin. The program's first step is to use Google to find relevant websites to what it's researching. Now that the AI has found the GitHub repository for AutoGPT, it's opened it for analysis.
It's looking at the GitHub repo right now to find out about itself.
After scanning the website's contents, it has summarized them and will now place them in the AutoGPT.txt file we have opened. As we can see, AutoGPT can teach itself about different topics using the internet, allowing it to have a better understanding of the current world than ChatGPT.
All right. So for some of you, this may be scary. It's sort of like Skynet is released now to the internet, because the important thing about language is that's how we communicate with each other. That's how we interface. So, it can go ahead and language can be a command, right? It can be a command to search, a website or the internet or to get some other kind of information. So it's not just, these sort of cute little processing operations, but, for things like robotics later on.
Welcome.
Oops, get past here. It's can be able to do a lot more, and it can, hit the internet. One of the problems with ChatGPT, is trained in data from 2021, I think it was. It doesn't know about the new stuff, but AutoGPT can go ahead and pull that down from the internet and give you a good answer with the latest news. So what about possible healthcare applications for people who are interested in that? There's too many to list. It did not take me very long to kind of throw this up. All the training that we do, we have to worry about cheating a lot more now than we ever have. Certainly computer science, I know we're very worried about that. But you can do summarization, chart review, that could be a lot faster using these kind of tools. All the billing and coding, that's partially automated already, but it could be a lot better. And you may even get, summary reasons as to why something was billed that way. That might be nice in some cases. My boss, Jim Cimino, he has used it for recommendation letters, put a few things in the prompt and about the person, and then it spit out the rest of the kind of boilerplate text. I've heard it been done for insurance pre-approvals by physicians. Some of you may have done that. Maybe systematic reviews, you can do better, paper editing. And then with the multimodality, there's all sorts of robotic applications for healthcare. There's already robots kind of wandering around Japan, but they could be much better if they can process the environment using something like GPT-4. Also, maybe it can throw me out of a job. For fun, I threw up, a ChatGPT talk for this talk. I got about 8 slides out of it. You can take a look. If you think it's better than my talk, then I guess I'm out of luck. But another possible application for ChatGPT. So thanks. I used the Hugging Face a lot for this talk. Shan Chan also helped me quite a bit. And the GPT-2 and GPT-3 information came a lot from Jay Almer's blog. That was good. I should have cited every figure I have in the slides, but if I didn't, I'm sorry. Any questions or discussion for this? I think we have a little bit of time left. We have 17 minutes. Go ahead, Nadesh. Is it possible to distinguish between human text and ChatGPT text? Is your question? I guess that depends on who's doing the distinguishing. I think that the process where you generate that text and the process which you detect that text, they're very much in sync. And when things like reinforcement learning, it's just basically an arms race. So I think, I think it's very hard to tell. I think for some things, especially this, ChatGPT, it's maybe a little bit easier. May have a good intuition on it. But if your sample is very small, it's very easy to fool people. We know that from phishing already. You can generate text with something much more simple than, ChatGPT and still fool people and get them to hand over their credentials or whatever else. So I think it's an arms race. Yeah, no, that's not going to help very much. And I think we may get the situation, if we're not already there, where it's like email, where like 99% of email is spam. It's just mostly filtered out. So most of the web will end up looking like that as well. And that's, that earlier hype thing I showed where that scientific magazine, I can't remember the name of it, Clark's something, I can't remember. But they can't even accept submissions anymore because there's so much junk out there. So I don't think there's an easy answer to that problem at all. Sure. Zero GPT. I haven't heard of that one. How does that work? And do you know how well it works or what its capabilities are? He's saying for people that are online that can't hear, he's saying there's a tool called Zero GPT, which can identify, I guess any kind of synthetic text or just from GPT or ChatGPT? From ChatGPT. Okay. Yep. Yeah, I wouldn't be surprised that you can identify it, but I think also they're going to update, ChatGPT with, they're already working on GPT-5. So we'll have to see how well it holds up. Go ahead. Yeah. So that's another really good question. Yeah, so the question was sort of my thoughts on plagiarism detection and what the impact of ChatGPT is going to be on that. So I think we're still struggling with that. So I teach for mostly CS students, and so we're actually going to discuss this next month, some possible approaches to deal with this. To a certain extent, there's a lot of cheating already. Just makes it a little bit easier now with ChatGPT. So maybe we'll have to try Zero GPT, I guess, so that could potentially help us out a little bit. But I'm pretty sure that's going to be a stopgap solution. What I think may be happening is we may see a return to sort of the older style of student evaluation, where it's much more qualitative, that you're actually talking to the person supervisor and asking about that person, how hard are they working, what do they really know, rather than relying on a bunch of test scores. And I think we're kind of already moving in that direction as it is, because when you're evaluating a graduate student, I look at the scores that they have on, from coursework, and it's very hard. It does not have the best correlation between how good that student is going to be and how well they do in the courses, which is, unfortunate, but it just really means you have to really interview them hard. I think things like Google, they always have these ridiculously hard interviews. I think we're going to have to rely on, maybe better interviewing and more word of mouth. Which is bad in some ways because it makes it more of a, kind of a closed boys network where, hey, is this guy a good guy or whatever. But with the potential for cheating that is out there now, I think that's the direction we're going to move towards. Any other questions? Question? Go ahead. Prompt engineering, yep. Yep. Right. So there's different ways of doing prompt engineering. So I think the sort of first path that people had, I've done this myself, is sort of manual engineering of prompts. And I've had some success with that, but it's, there's not a lot of feedback that you get. So some people looked at this a little bit more systematically. They've actually tried, different series of prompts. And if you look at some of the results, it turns out that the prompt actually, useful prompts don't necessarily have any correlate into like what a normal English language prompt you would think has. So you may use bizarre series of words. There's a number of papers out there now that show, that the prompts you get aren't the ones you would expect or would like if you were doing an English language prompt. There's also libraries out there now that'll do all that work of prompt engineering for you. It's basically just another hyperparameter in your model that you're going to tune. And so if you want to do prompt engineering, there's definitely tools for doing that now. But they're weird, and they're not something that as a human you may expect you would get. Curtis. Well, I can say you could read the GPT-4 paper and how they incorporate the vision with the text, but of course they don't have any of those details. My understanding is that most of the models that do incorporations are still using transformers. You may use, convolutional neural networks as well in vision. Those are very important. But I don't have any, I can't tell you how that, the GPT-4 working or how you do that multimodality. Okay. Oh, one more question. Go ahead. Right. So, I mean, I think the question was, do you think it, there could be like a game basically between ZeroGPT and the ChatGPT trying to fool each other? Was that the question? Yeah. So, yeah, I don't know how ZeroGPT is trained. I don't know if was it actually trained using that sort of reinforcement type learning that you had? Okay. So I guess the answer is yes. That's probably how actually they got ZeroGPT to work. So, yeah. Any other questions? Okay. Well, thank you very much for listening, and thanks, Jake, for inviting me to this talk.